Continuing with our discussion on the summation of sine waves and harmonic series, we're going to talk about square waves and our triangular waves again. So over here we have 4 sine waves, S1, S2, S3, and S4. They have different frequencies and different amplitudes, but identical starting phases. Let's say the frequency for S1 is 100 Hertz. You see how it has completed one full cycle of vibration? Now, how many cycles of vibration has S2 completed? 1, 2, 3. So the frequency for S2 is 300 Hertz. And S3, let's count. 1, 2, 3, 4, 5. 500 Hertz. And I can take a guess that S4 is 700 Hertz. So we have a wave of 100, a wave of 300, a wave of 500, a wave of 700. So they can make a harmonic series. There's a relationship between these waves. You have a fundamental frequency that is multiplied by whole number integer multiples, but they're not odd and even integer multiples this time. For a square wave, for a resultant square wave, we have the summation of odd integer multiples. So as long as there's an appropriate frequency relationship among those waves, we can create a harmonic series, a complex and periodic wave. Remember, to be periodic, there has to be a mathematical relationship between the fundamental frequency and the whole number multiples. And like I said, when we created the square wave, what we were doing was adding just the odd integer multiples. Here's an example if a fundamental frequency were 1,000 Hertz. So 1,000 times 3, 1,000 times 5, 1,000 times 7. All of the sine waves that get added to create the square wave are odd integer multiples of the fundamental. There's another example with a fundamental at 400 Hertz. So this is different from a sawtooth wave, because now we're just multiplying by odd integer multiples. And you get a complex, because it's not just one wave, it's a bunch of waves added together, periodic, because it repeats itself wave. The phase in these examples has been consistent, but we'll see later on how if the phase is different, the wave also becomes a bit more complex. Going back to our sawtooth wave, remember there was a fundamental frequency, and then the harmonics were odd and even integer multiples. So let's say S1 is 100 Hertz. S2 is therefore 200 Hertz. S3 is 300 Hertz. There's a harmonic relationship. We have odd and even integer multiples that are summed together to create the sawtooth wave, and that's the wave that we have for our speech. So when an infinity of odd harmonics with appropriate relative amplitudes and starting phases are summed, you get a square wave. When an infinity of odd and even harmonics with appropriate amplitudes and phases are summed, you get a sawtooth wave. In this example, what's different? Look at these waves, the solid wave and compare it to the dashed wave. So the starting phase was identical in our past examples, But in B, C, and D, we have different starting phases. And you see how the waves get even more complex and different by varying the starting phases.